42nd lecture, and we continue our discussion on widebanding techniques. We have already learned how to use an inductance for widebanding. Today we study widebanding by using compound devices, that is more than one device connected in a suitable fashion. And one of these, as we have already discussed while discussing tuned amplifiers, is the CCE combination, CCE, in which the effect of C mu is minimized. That's what we discussed? Or okay. Then we will discuss now a CCCE combination, one, and the other is a CE CB combination, common emitter, common base. CE CB combination, which is also known as, which is also configured in the cascode configuration, that is, the common base sits upon the common emitter. Okay, first we take the CCCE combination, and the actual circuit shall look like this. You have a VS RS, then you have the transistor Q1, it is a common emitter transistor, and usually in integrated circuits the biasing is done through a current source, This is the DC bias. This current source could simply be another transistor held at a certain base current, fed with a certain base current. Okay, we shall assume that the equivalent resistance of this current source is RE1, which is, as you know, is very high. Okay, then this is a common collector. In other words, for AC this is ground, common collector, and therefore the coupling is to be through the emitter. I don't want that murmur. In addition, there may be a biasing resistance here. From the supply there may be two biasing resistances, so the AC equivalent circuit would give you an R sub B. Okay. This is then fed to the common emitter. The emitter is grounded and the load is in the collector R sub L. This is also grounded and the output is taken from here. This is my V0. And this is the compound device, two transistors which is available as a chip, a CCCE combination, Q1 and Q2. And the reason why this acts as a broadband amplifier is not difficult to imagine. This is usually available as a chip, where sometimes even the component of RE1, the current source, is also integrated inside the chip. Okay, it's a wideband chip. Motorola has this and several other companies have this. Now the reason why this is a wideband device can be easily guessed. You see, as far as C mu 1 is concerned, C mu 1 is virtually connected to ground across RB. So C mu 1 therefore is virtually grounded. Now as far as C mu 2 is concerned, well, it will be from here to here and it shall have an effect. Let us see what the effect is. The equivalent circuit, you have to draw it very carefully. The equivalent circuit is like this. You have a VS, RS, RB, then you come to the base of Q1, and from the base of Q1 to ground there shall be the capacitance C mu 1, then R pi 1 and C pi 1 shall not go to ground. R pi 1 and C pi 1, they are connected to RE1, and in addition the base of Q2 to emitter, that would be R pi 2 and C pi 2. But before we go further, let us look at this voltage. This voltage is V pi 1 with this polarity V pi 1, and therefore there is a GM1 V pi 1, a current source from the ground, the collector is grounded, to the emitter, GM1 V pi 1, and if this voltage is considered as V pi 2 plus minus, is the polarity all right? From B2 to ground, that's right, from B2 to E2, the polarity is all right. Then you have the C mu 2 which goes to the collector, and from the collector to the emitter, that is to the ground, there shall be a GM2 V pi 2, GM2 V pi 2, and what else? We shall have an RL, of course, that goes to ground. Anything else? That is the end of it, V0. Okay. Now, have I missed anything? No. Now, you can decouple the input and output of this through Miller effect, and therefore you can write C mu 2, you can bring C mu 2 here as C mu 2 1 plus GMRL, the usual way, and have a C mu 2 here if necessary. If C mu 2 RL is not very small, have a C mu 2 here. You also can combine these two resistances into, let us say, a resistance RE. Let us call this an RE. Then, is there any other combination possible? C pi 2 can be combined with CT2, all right. So, my equivalent circuit, simplified one, shall look like this. I have a Vs, Rs, then Rb, C mu 1, R pi 1, C pi 1, voltage is V pi 1, this goes to Re, and a capacitance Ct, where Ct, what did we do with R pi 2? R pi 2 is combined with Re1. Okay. Ct is C mu, I beg your pardon, C pi 2 plus C mu 2 1 plus GMRL. Okay. This is V pi 2, and then you have the GM V pi 2, then an RL. GM2. C mu. Oh yes, okay. There is a C mu. And this goes to V0. Anything else that you have missed? GM1 V pi 1, yes, that current source must come here. GM1 V pi 1. This goes to ground. Now let us make some obvious conclusions which will be required later. If I look here, what is the input resistance, mid-band input resistance? It is R pi 1 plus beta 1 plus 1 times Re, mid-band. So this is, we require this because we will calculate the time constants later. Okay. This is R pi 1 plus beta 1 plus 1 times Re, mid-band input resistance. And if for a moment we bring, okay, if for a moment we say that the mid-band input resistance here is Ri, then obviously Ri is equal to Rb parallel Ri prime. All right. Let us call, what is this point? This is the base of transistor 1, B1. So, let us call this voltage as VB1. Then the mid-band gain analysis is extremely simple. Mid-band gain analysis, just by looking at this amplifier, looking at this equivalent circuit without deleting the capacitances, you can very easily see what the mid-band gain would be. For example, V0 by V pi 2 would be minus GM2RL. Okay. Then V pi 2 divided by VB1 would be beta 1 plus 1 Re divided by R pi 1 plus beta 1 plus Re and VB1 by Vs would be Ri divided by Ri plus Rs. Therefore, the mid-band gain AV0 would be equal to minus GM2 RL, I write by inspection, multiplied by beta 1 plus 1 Re divided by R pi 1 plus beta 1 plus 1 Re multiplied by Ri divided by Ri plus Rs. That is it. That is the mid-band gain. And you can see that in usual practice R pi 1 would be a very small quantity as compared to beta plus 1 Re. Therefore, this will be approximately equal to 1. This factor, since it is a voltage source, Rs would be small compared to Ri, and therefore this factor is also approximately 1. In other words, the gain of the compound circuit, the mid-band gain, is virtually controlled by RL and GM2, nothing else in this circuit. Okay. The next question is that of finding out the high frequency 3 dB point. This is of major concern. We want to find out what is the high frequency 3 dB point and see to what extent we have achieved broadbanding. For that, you see, if we go back to the equivalent circuit, this is CMU2. There are, even with simplification, even with Miller simplification, I have 1, 2, 3, 4 capacitors. If I did not do Miller simplification, I would have
3.
No, 5. If I did not do Miller simplification here, I did not have to do it here because CMU1 comes in parallel with RB. Why 5? 1, 2, there would have been a C pi here, C pi 2, then CMU 4. Okay, I stand corrected. If it is there, we are not considering that. But anyway, this is bad enough. No, 1, 2, 3, 4. So we don't increase by any. You don't increase the number of capacitance, isn't it? There is no strong point, therefore, in calculating FH to take recourse to Miller effect. Is the point clear? Miller effect itself is an approximation. Now, I can calculate FH from this equivalent circuit, which is the Miller effect equivalent circuit, but since the number of capacitors is not decreased, therefore, there is no point, not much of a point in calculating FH by using Miller effect. We could as well go back to the original circuit and replace this by C pi 2, bring a CMU2 here and take CMU2 off from there. Either way, this is slightly simpler because there is no cross connection, because this time constant is simply CMU2 times RL. Okay, it's slightly simpler, but one can calculate the other way also. Let us calculate from here. Now, if you want to write the exact equations, you see C pi 1 CT, they are coupled together, and of course this part can be written very simply, but this part will require a coupling of 3 capacitors, CMU1, CPi1 and CT, and therefore it would be very, very involved. And the method of open circuit, is it open or short? Open circuit time constants is a better way to deal with FH of this circuit. And if you recall, in the method of open circuit time constants, what we have to do is we have to find FH as 1 over 2 pi summation tau I. Is that the method? Where summation tau I here would be CMU2 times effective resistance across it, R mu 2, plus CT2 RT2, we are going back, plus C pi 1 R pi 1 plus C mu 1 R mu 1. I have not yet found out these resistors, we will have to find them out. Okay. Now, as far as R mu 1 is, no, R mu 2 is concerned, we have already seen R mu 2 is equal to RL. Okay. We also know what is R mu 1. Let us go back to the circuit. R mu 1 would be simply RB parallel RS. What about from this side? That is Ri prime. Okay. So it would be Ri prime plus, not parallel, or parallel? Parallel. Okay. So let me write that down immediately. R mu 1 would be equal to, why don't we take Ri parallel RS? It's the same thing? Okay, Ri parallel RS. Now, the other two are not very simple. For example, to determine R pi 1, we have to draw the equivalent circuit with all capacitors open, and resistance has to be measured across C pi 1. So let's see the equivalent circuit. If you short Vs to ground, you shall have Rs prime, which is equal to Rb parallel Rs. Okay, Rs prime. Then you shall have R pi 1. It is across this that you want to measure the resistance, because C pi 1 occurs here. Then you have Re to ground, and what else? You have a GM1 V pi 1. Well, you have to connect a voltage source here. Let us call this voltage source as V1 and let this current be I1. Then obviously GM1 V1, because that is the voltage across R pi 1, and this goes to ground. Alright. You have to measure the resistance seen by V1, this voltage source. In other words, you have to find out V1 by I1. Alright. And this can also be done by inspection. It's not a very complicated circuit, but one has to be a bit careful. Now the care that one has to exercise is the following. One has to recognize that I1 is, let me write it down, I1 is V1 by R pi 1, that is this current, plus let us say this current is I1 prime. Alright, I1 prime. Now what is I1 prime? To find out I1 prime, we write a KVL around this loop. There are many ways of doing this. I can argue that this current, what will be this current? This current, I1 prime, it has to be, I1 prime is coming out, so I1 prime must go in, and therefore what is this current? I1 prime minus GM V1. Therefore, my KVL would look like V1 is equal to I1 prime RS prime, this drop, plus the drop in RE, which is I1 prime minus GM 1 V1 times RE. Agreed? Which gives me I1 prime. Now, instead of doing this, people who are a little smarter could argue that this parallel combination could be converted to a Thevenin source. Then you have GM1 V1 RE in series with RE. So it was a single loop circuit, and the current I1 prime could be obtained by inspection. It would be, tell me what is the inspection? It would be V1 plus GM V1 RE divided by RS prime plus RE. And this would not have required writing the loop equation at all. It is by inspection. And therefore, whatever you do, you see that V1 by I1 shall be the parallel combination of R pi 1 and the resistance, which would be RS prime plus RE divided by, does it look like I am 1 plus GM RE, GM1 RE, isn't that right? Okay, so R pi 1 is equal to small r pi 1 parallel RS prime plus RE divided by 1 plus GM1 RE. Once you identify the equivalent circuit, it's a very simple equivalent circuit, but you have to proceed with caution. It is not R pi 1 parallel RS prime plus RE, because there is a controlled source there. It's very easy to make that mistake. You make that mistake saying, oh, current source, it is infinite impedance anyway, but it is not an independent current source, it's a dependent one, and therefore that contributes. In fact, the equivalent resistance is reduced by a large factor, GM1 RE, 1 plus GM1 RE. Okay? It's very easy to make a mistake here, so I calculated this exactly. The other calculation that is needed is for RT2, that is the resistance seen by CT2. If I draw the equivalent circuit for RT2, well, we come from the input RS prime, which is the same as done as defined previously, RB parallel RS. Then you have an R pi 1, the voltage here is V pi 1 plus minus. Then you have a GM1 V pi 1 from ground to this point. Then you have an RE, and it is across this that CT appears, CT2, and therefore what you do is connect a voltage source here, V plus minus, and find out this current I. RT2 shall be equal to V by I, V by I. Alright, RT2 shall be equal to V by I. Now, I obviously is equal to V by RE, the current that goes here, minus GM1 V pi 1, then another current comes like this, so minus V pi 1 by R pi 1. That's it. And finally you have to find out V pi 1, because this is the unknown, and if you write KVL, this V should be equal to drop in this plus drop in this. So V is equal to minus V pi 1, right, then minus the current through this is V pi 1 by R pi 1 multiplied by RS prime. So you can find out V pi 1 from here, substitute here to get the equivalent resistance. If you clear this algebra, then the equivalent resistance RT2 comes as RE parallel R pi 1 plus RS prime. Again, it's very easy to make this mistake. It is not the parallel combination of this, but this comes reduced by the factor 1 plus beta 1. Okay, and that's it. What else do I have to calculate? I know R mu 1, I know R mu 2, I know C pi R pi 1, and I know RT 2. These are the 4 capacitors, and therefore I can calculate my tau by summing up all this and tau sub I and FH, which is equal to 1 over 2 pi tau. Let us take a specific example. I will not write this again, the whole expression. You can collect them and collate them. Let us take an example in which the current source is a poor current source. Okay, RE1 is equal to 4.3 K. The current source is not a good one. Okay, or maybe it's a lumped resistance 4.3 K. To see how good things are. You see, if RE1 was was a good current source, then instead of RE we should have had simply R pi 2. This RE has a shunting effect. Now, is it good or bad? Do we want low value of resistance or high value of resistance? Pardon me? We want a low value. Isn't that right? 1 over tau. So, the lower the value of the resistance, the higher would be the cutoff frequency. On the other hand, if it's an IC chip, the biasing is preferred to be done by a current source. Why? Because you don't require extra resistances. All right. On the other hand, if you want a lumped resistance, you can use as small a value as possible. But anyway, let us say the current source is such that RE1 is 4.3 K. Yeah.
What is the cause of widebanding in this circuit?
What is the cause? Because of the cutting of CMU1.
CMU1?
Yeah. That's right. There is a decoupling between the input and output through CMU1. CMU1 is grounded. Okay. Now, let us go through the calculation, then we will see how good or how bad it is. Now, RS is 4K and RB, the usual story, is about 50K, the biasing resistances. The two currents IC1 and IC2 are equal, both of them are 1 milliamp, which means that GM1 and GM2 are equal, and they are equal to 40 milliampere per volt. Okay, 1 divided by 25.04 millimole, so 40 milliampere per volt. The beta 1 and beta 2 are given as 100, and therefore R pi 1 and R pi 2 2.5 K. In addition, the transistors are identical transistors, they are made on the same chip, and maybe a million of them. CMU1 and CMU2 are both 2 puff, and FT, the transition frequency, is given as 400 megahertz. This means that you have to find out C pi 1 and C pi 2. C pi 1 is equal to C pi 2 is GM divided by, remember this, GM divided by omega T minus C mu. Okay, GM is 40 millimole. Is it 40 millimole? Yes, 40 millimole, and omega T is 2 pi times 400 times 10 to the 6. From that you subtract C mu, and the result is 13.9 puff. You recall this formula. Many a time C pi shall not be given. What will be given is FT, but C mu is required. If C mu is not given, what will you do? Ignore it. If it is not given, assume it to be 0. Good strategy, yes. In addition, what else do you need? You need an RL. RL is given as 2K. Then I have calculated all the intermediate steps. Let me simply give you the results. The first thing you do is calculate RS prime, which is RS parallel RB. This comes at 3.7 K. These are calculated values now. RE is 1.58 K, which is the parallel combination of RE1 and R pi 2 RE. Then R sub I, parallel combination of RB and R pi 1 RI dashed. Okay, this comes out as 38.2 K. R mu 1, which is the parallel combination of RS and RI, that is the resistance in by C mu 1. This comes as 3.62 K. Then R pi 1, which is the resistance seen by C pi 1, parallel combination of R pi 1 and RS plus RE divided by 1 plus GM RE. This comes out as a low value, 0.08 K. RT2, which is the resistance seen by CT2, is also a low value, 0.059 K. Okay. You require CT2. CT2 comes as 175.9 puff. The mid-band gain AV0 is calculated from inspection of the equivalent circuit as minus 78.8 by taking everything into account, whereas the approximate value is minus GM2 RL. This will be minus 40 times 10 to the minus 3 multiplied by 2 times 10 to the 3, which is equal to minus 80. So it's not too bad. Okay, minus 80 is a fairly good approximation to minus 78.8. And FH, by calculating all these time constants and clearing of fraction, FH comes as 7 megahertz. So the gain bandwidth product is, if you multiply 7 megahertz by 78.8, this comes at 551.6 megahertz. Gain bandwidth product in hertz. Compare this with FT. FT is 400 megahertz. Okay. The GBW therefore exceeds the FT of a single transistor. By using two transistors in this particular configuration, you can go to a gain bandwidth product of 551.6 megahertz. If only one transistor was used, you could not go beyond 400 megahertz. Okay. In fact, 400 megahertz you could go only with current gain. Alright. If current gain is 1, then the bandwidth would be 400 megahertz, and that is the condition for short circuit current gain. The actual gain bandwidth product would have been much less than 400 megahertz. This is how widebanding has been performed. The second circuit is a more interesting circuit. Once again, we have talked about this while talking about tuned amplifiers. This is the CE CB configuration, or the so-called cascode configuration. The circuit is like this. You have a VS, RS, Q1. This is grounded. This is the common emitter. And then you have a common base sitting on it. Another transistor Q2, whose base is virtually grounded. Okay. And the load is on the collector of Q2 RL. I have shown the AC equivalent circuit, and this is my V0. Q1 is a common emitter and Q2 is common base. So it's a CE-CB combination, or a cascode combination, because Q2 sits upon Q1.
We have an RB also.
You have an RB, okay. The base is usually biased like this. Yes, you are right. There would be an RB. The base is usually biased like this. Let's say, it's a good question. let us say this is Q2, okay, Q2, then this goes to Q1 and this is the other base. Now both the bases have to be biased. So what is done is plus VCC, a resistance is brought here. Then this resistance should have gone to ground, but we want this base also to be biased. So what we do is we split this into two parts and connect this base here. Okay, this is the actual biasing arrangement, and therefore from this base there should come a resistance R sub B. Now this base is not connected to ground, whereas we want it connected to ground. So what we do is we connect a large capacitor from here to ground. That will mean that if this resistance is R3, this is R1, this is R2, then RB would be the parallel combination of R1 and R2, because this is virtually grounded. Is the point clear? This is how it is made. But the IC chip that is available is this, is the one that is contained within this blue area. The IC chip that is available. It is available. This has to be, this cannot be connected to ground inside the chip, because you have to connect a high value capacitor. So this is out, and the pins are marked. This is B2, this is C2. These are not brought out. There is a B1 and an E1. Okay, the collector and emitter, the collector of Q1 and emitter of Q2 are internally connected to each other. This is the chip that is available, cascode chip, the CECB chip. Now, how it achieves? Okay, first question that I ask is, what is the relationship between the GMs of the two transistors? They should be the same. If beta is large, then IC2 and IC1 are approximately the same, if beta is large. Okay, and therefore GM1 and GM2 are approximately the same. Now, at midband, what is the load seen by Q1? The load seen by Q1 is R phi 2 divided by beta 2, which is equal to 1 by GM2. All by inspection, I am not analyzing anything. 1 by GM2. Okay, 1 by GM2. Then what is the gain of this circuit? Q1 minus GMRL. So minus GM1 multiplied by GM1 by GM2. So the gain would be, gain of Q1 would be minus 1. Agreed? It is like an emitter follower, but with a gain of minus, negative. Okay? It's an inverting, not emitter follower, it's an inverting buffer. Inverting buffer. Okay? Therefore, the C mu 1, now follow me carefully. The C mu 1, which appears between B1 and C1, shall be reflected at the input as what? C mu 1 multiplied by 1 plus GMRL. So it would be 2 C mu. Is that correct? Instead of getting multiplied by GMRL, which may be a large quantity, because we have restricted the load of Q1 to be a very small quantity, 1 by GM2, and because GM1 and GM2 are equal, only twice C mu 1 comes in. And that twice C mu 1 also is reflected across C pi 2. Isn't that right? So C pi 2 will be incremented by twice C mu 1. Alright, now let us go into this circuit, into the exact equivalent circuit, and see what the gain is and what is FH. Well, as far as
Sir, it should be only C mu 1.
C pi 2 is here, from here to here.
But we are talking about the input side.
No, input side it is twice C mu 1, but as far as this side is concerned, instead of This requires an explanation. Instead of it should be CMU1? No.
CMU1 plus CMU2. Because CMU2 would also be coming in parallel with CMU1.
CMU2 is from collector to ground.
No, if you do Miller approximation there.
No, that would not come there. You see, it would simply go, CMU2 would simply go across RL. But you can see that there is C pi 2 between this point and this point. Alright, which will be supplemented. See, C pi 2 is virtually 1 by GM2 parallel C pi 2 is the load of Q1. Alright, so C pi 2 in the previous case in a common emitter transistor RL was supplemented by CMU2.
Where is C pi 2? C pi 2 is not between the emitter and
C pi 2 is from the base to the emitter of Q2 and reflected on the emitter side it would be C pi 2 multiplied by no, multiplied by beta. Isn't that right? You had divided R pi 2 by beta and that's how you got 1 by GM2. So if it is C pi 2 then it should be multiplied by beta. So it's a larger capacitance and twice CMU1 across is negligible. Is the point clear? Okay. Let us see the exact equivalent circuit, then perhaps things would be clear. Oh, the other thing that I wanted to explain to you, not only the Miller effect of Q1 is reduced to twice CMU1 only, the Miller effect due to Q2 is absolutely absent. Nothing is reflected to the input side because the collector, the CMU2 appears between collector and base, which is grounded. And therefore, the CE-CB cascade is an extremely popular combination for wideband amplifiers. And the equivalent circuit, it will not come in one page, so I will bring it down. I will try to compress it as much as possible. But if you cannot see it, please do point out. What we have is Vs, Rs, then an Rb. Then I should go to R pi 1. But in high frequency analysis, sometimes RXs do come into effect, particularly when the capacitors are small. Capacitors are large. Now in this particular case, it is convenient to be able to take care of RX1. It is possible. So let's do that. You will see why. RX1. Then we have the B1 prime, the internal base, and so we have R pi 1 which goes to ground, C pi 1 which goes to ground, and this voltage is V pi 1. Then we have CMU1. We will come to Miller effect equivalent circuit a little later. CMU1, this goes to collector 1 which is the same as emitter of 2. From collector 1 to ground to emitter 1, there shall be a current source GM1 V pi 1, and from the emitter to ground, well, let's bring it over here. I can't go this way, and it's important to recognize this circuit. Don't make a mistake. From base 2, which is ground, from B2 there shall be a resistance of R pi 2 with the voltage V pi 2 of this polarity. Agreed? Then from R pi 2 there shall also be a capacitance C pi 2 which you have been talking about. Alright. Then this is base 2. From base 2 you shall have to collector 2. You shall have a capacitance of C mu 2. This is collector 2, C2. And from collector 2 to ground, you shall have a resistance of RL. Alright? Current source is from C2 to E2. You see the complication? Current source is this, GM2 V pi 2. This is the equivalent. I have gone exactly according to the architecture.
So C mu 2.
Yes.
has ground on either sides.
No, no, it's only on this side. C mu 2 is from C2 to B2. B2 is grounded. But on this side it is RL which is grounded. Agreed? RL is on the collector 2, from collector 2 to ground. Okay. If there is no question, if this is okay, then you should recognize that the first simplification that we can do is that the circuit to the left can be converted to its Thevenin equivalent, and therefore this would be some Vs prime in series with a resistance Rs prime. We can do that, and you can very easily find out what is Vs prime. Vs prime, first application here, Vs Rb by Rb plus Rs in series with Rb parallel Rs, then Rx1, then R pi 1, and therefore things are absolutely clear. Okay, the second simplification that we do is to look at the last part of this. Alright, now you see we will play a trick, but perfectly valid trick. We have not played it so far. Let's do it now. You see, as far as E2 is concerned, we are looking at this part of the circuit, the lower part of the circuit. Alright, you will see how we simplify. As far as E2 is concerned, E2 sees a C pi 2 to ground and what else? R pi 2, okay. Again R pi 2 to ground, and at this point there comes, what is the voltage across this? V pi 2 with what polarity? Plus and minus. And at this point, as far as the point E2 is concerned, there is a third connection, and that connection comes from a current source whose value is Gm2 V pi 2. Okay, this current is to be equal to Gm2 V pi 2. Now instead of a current source, because the voltage here is V pi 2, I can use a resistance here whose value is 1 by Gm2. Is this trick clear?
No, sir.
No? Instead of the current source, well, what we have done is we have replaced the current source by a resistance. How can you do that? If the current source depends on this voltage, V pi 2, obviously all we care about in writing KCL, KVL or whatever it is, what current is coming. The same current will come if we include a resistance of 1 by Gm2. And that's the trick.
So but the voltage 1 by Gm2 should be in series with the parallel combination of RL and CMU2.
Yes, sir.
Well,
It's not directly across the current.
Because it is not going to ground.
right, we'll come back to this. So if you are taking care of the node E2, you should also take care of the node C2.
Yes, sir.
Yes.
Okay, because the current source is between E2 and C2. So let's be fair, we have considered E2. As far as E2 is concerned, there is nothing wrong with this. But we must now take care of C2. Now at C2, let's look at this terminal C2. At C2, we have a C mu 2 to ground, agree? And an RL to ground.
Right, sir.
In addition, well, this voltage is V0. In addition, we have a current source coming out of C2, and this current source is Gm2 V pi 2. Okay? Does it matter where it goes? So long as a current is extracted from here, it doesn't matter where it goes. Right? Is the point clear?
So what we have
V pi 2 is not here. V pi 2 is not a voltage in this part of the circuit. There is a current which is extracted from the node C2. I don't care where it goes. I can leave it like that. I can connect it to ground. I can connect it to a resistance and then to ground. It doesn't matter. All that I am concerned with is that V0 would be equal to minus Gm2 RL parallel 1 by J omega C mu 2. And then we can forget about the output circuit. Is the point clear? the current GM2 V pi 2 must come from the parallel combination of RL and C mu 2. Once we have taken care of this, we forget about the output circuit. Alright, this is the trick.
So what about the resistance 1 by GM2 R? GM2?
1 by GM2 was necessary at E2 because we had to take care of this current.
So the voltage drop across that is V by 2.
That's right. It is V pi, that's how we could replace it by 1 by GM2. The voltage is V pi 2, therefore the current through this is GM2
So
V pi.
is the voltage really V by 2? Because across the current source you don't know the voltage.
I don't
think
care.
It is V0 plus V by 2.
I don't care. I only include this current in this circuit. That's it. There is a current source GM2 V pi 2 and I have a voltage V pi 2 and therefore I connected resistance 1 by GM2. The current source has been completely taken care of. And this is a trick. This is an equivalence theorem. There is a name for it in the literature, but we don't want to go into that. But this is a trick. And with this trick, you see the output circuit can now be completely forgotten. Even the input circuit, the current source is taken out, replaced by a resistance. And now you can combine R pi 2 with GM2, 1 by GM2.
Excuse me, sir.
Yeah.
Sir, but from the point C2 to E2,
C2 to E2.
I have a voltage drop of V0 plus V pi 2.
I have a voltage drop of V0 plus V pi 2. No.
Yes, sir.
Sir, in the actual circuit, the previous one.
No, it's not. This is V0
Yes, sir.
plus minus. Okay, and V pi 2 is the opposite polarity. Yeah, fine.
So I have a voltage drop of V0 plus V pi 2. Do I take care of that voltage drop in the equivalent circuit? The simplified trick circuit.
So, simplified tricky circuit. It's not necessary. I am not measuring between C2 and E2. I am only measuring the voltage across RL. Isn't that right? You see, I am measuring the voltage across RL. So, as long as the voltage across RL is the same, I don't care.
Whatever be the voltage.
Whatever be the voltage, that will take care of itself. Alright, agreed? The trick is valid. Do apply the trick whenever you get into a tricky situation. I think this is a good point to stop. We'll continue this next time.